All right. Welcome, everyone. Today, we're going to be talking about working with data. I know in our curriculum, currently working with data is part two of the lecture we did on Friday that will get adjusted. As we saw, the lecture on Friday was a little bit longer than expected, so these two will stand as their own standalone lectures. But before we go into lecture, let's do a little bit of recap over what we've done so far, right? So here I have the drawing that we came up with on Friday morning, where we talked about our neural network. And it was brought up to my attention that we've been talking about this neural network in several different ways, but we haven't really talked about what it is that our neural network is doing. So let's start off our day by talking about a scenario, right? In this scenario, what we're trying to accomplish is, let's say we're working for a water department, and this water department is in charge of making sure that water is actually drinkable or potable, right? If it is drinkable, then we want to train our learning model to actually tell us true, hey, this water is drinkable, or tell us false if this water is not drinkable. Now, why implement a learning model to do this thing in the first place? Well, think about the amount of people that it would take to collect all of this data, right? So we're already spending resources and money on people to collect data. We're spending resources and money on all kinds of research and distributing this data. So why not create an efficient way to actually run this data and tell us, hey, this is true or false. Rather, I'm assuming that if this is a real world organization, they wouldn't just depend on a learning model. I'm sure there's an actual human checking against the learning model itself. But that's the scenario we're looking at, right? And if we want to take a look at some data here, here you go. I'm going to go ahead and share this link here on the X-ray questions channel as well. So here's our water quality data. Right, somebody went out there and they collected all of this information regarding pH values, the hardness, solids, each one of these attributes or these features uh, that essentially describe our object that we're trying to evaluate to be either true or false. And all of these features come up with a label, right, or a result, which is potability, which indicates if it is, in fact, something that's fit for human consumption or not. And if we take a look at the data down below, they've done most of the analytics for us. We saw this in Erica's demo, where we were talking about overrepresentation. We were talking about standardization and normalization when it comes to data. And you can see they have a graph for each one of these to show everybody the general spread of the data, right? There's not really any weird spikes or anything being necessarily overrepresented here. But there is a couple of things that we have to consider, right? So if we come over to our results, we can see that the majority of our results are actually false. And only about half of what is false will evaluate to be true. Additionally, we also have to consider the fact that this data schema is accounting for no values, right? Or not accounting for no values. So there's no values that are being placed into the schema like we saw in a database, right? We're accepting blank or null values. And that's something that we also have to account for whenever we're training our model. So these are the features or the characteristics of my water, which I will feed into my learning model. And then I will ensure that my learning model either returns a 0 or a 1, letting me know that a water is drinkable, right? So now let's break that down. If I were, let's say this is our data, right, being passed into the input, well, what would that look like in our binary classification here? Data gets passed into the input, all the attributes that belong to the water, right? Each one of those attributes or each one of those numbers between 0 and 1 gets passed into its own neuron, which is just one of these circles. And each one of these neurons has its own weights and biases, where our weights tell us how to communicate with the next layer of neurons. And our biases are there to ensure that our weights are actually within a certain limit to ensure that they are actually able to communicate with the next layer, right? So our biases is more, should we talk or should we not talk? While our weights is, how should we talk to the next layer of neurons, right? So we see it go through, it goes through the first layer, our weights and biases are applied. It goes through a secondary linear layer where it takes the output of the first linear layer, applies weights and biases again, and outputs a singular neuron, which ideally we would want to be between 0 and 1 for our binary classification. Well, how do we ensure that number is between 0 and 1 and that it's squished and mathematically applied correctly? Well, that's where our activation function of the sigmoid layer comes in, right? So our activation layer has the sigmoid function. It takes in that singular neuron, runs the mathematical operation where it squishes it to ensure that it's between 0 and 1 and that it's a balanced output so that it doesn't give us incorrect information. And that gives us our output. And then our output is simply an if statement saying, hey, is this greater than 0.5? If it is greater than 0.5 or greater than or equal, I apologize, greater than or equal to 0.5, then we know the water is potable. If it is not, then the water is not potable. All right, and that's our binary classification there. All right. Does anyone have any questions over that recap of the material that we have up to this point? Let's hear it, Mama.
Yes, sir. In term of the example of the water, okay, we have different kind of data. If we were gonna put this data on this linear layer, so how are we gonna represent it here as an
How
input?
got it as the
Like,
input.
yeah,
Yeah. So essentially, and we'll be working through this today. So essentially what we're going to do is we have the water potability data available to us, right? And what we're going to do is we're going to create tensors for each one of these attributes, with the exception of the water potability, right? And each one of these attributes or numbers is what gets fed into each neuron inside of our linear layers. Does that answer your question, Mama? Okay, I see the
yeah,
head
thank you.
nods, of course. All right, so let's get into cleaning up our binary model a little bit, right? So first I'm going to go ahead and import torch. I'm going to say from torch, import nn as nn. And from torch, I want to import tensor as well. And I believe that is all we have up to this point. It's just the NN library working with us. So let me make sure that this is executable. And let's go ahead and make sure that we have torch working by printing torch.version. All right. So there you go. We know we have PyTorch installed. We can do torch version. And let's talk about our model. So binary model for working with water quality data attributes. All right. So this is what we'll be building. We're going to go ahead and build a model that will take in our code or that will take in this amount of features and output a true or false statement. So with that said, currently, well, let me go ahead and start off by giving us a template here. We're going to start building our class, which is going to be our binary model. This is going to utilize the NN module. And then just like everything in OOP, we need an init method. Oh, hello. that will initialize the class itself and its inherited class. All right. And then we're going to need to specify how we want to apply our forward pass. Okay, so there's our two methods that we need to make sure that is applied for our model, right? Now, just real quick, we know that our model is going to be a binary classification model. We understand that we need to build linear layers. And in this case, we're going to go with 2 linear layers. And let's go with 3 actually, just to stick to the 2/3 rule for now and make sure that we're accurate on our first go around. And we know we're going to need an activation layer. Now, for our activation layer, if we go back to our drawing here, we determined that what we wanted to use was the sigmoid function. And for our linear layers, well, these are just hidden layers. We know we're using a linear layers. We'll go over into activation functions within hidden layers later on. But for now, this is what our model looks like, right? Okay. So that's what we know about what we want our model to look like. What about our data? All right. How many features do we have? Or how many attributes do we have for this study? Anybody want to take a guess there? Let's hear it, Eric.
I think it would be 9, and then our output would be the 10th.
Yeah, perfect. So we have 9 attributes that we have to account for. Right? And we know that this binary classification model should account for 9 features. So there you go. There's our model. Let's go ahead and start building our layers. Like we said, we wanted 3 layers. All right, so these 3 layers, what would layer 1 look like if we're accounting for 9 features? Right, we know we need nn.linear. But what is the first parameter that would go into linear? Let's hear it, Daniel.
So I think we have to take in 9 attributes for 9 features. Then we want to spit out 8, and we want to make the other parameter be 8. So it'd be 9 comma 8.
Okay, yeah, we could do 9 and 8, definitely. And then you said that the other one would input 8, right? So you can
Yes.
definitely go down 1 at a time. In this case, I'm going to go down by 2. And then I'll go down by 4. And this is just because by the end of it, how many neurons am I supposed to output? All right, if we take a look at our binary classification model that we did here, how many neurons are we expecting to output?
Just 1.
Yeah, we just want 1. So I'm just cutting it down and outputting 1. Great. So there's my layers. What about activation? What would I place here from activation? Let's hear it, Orjan.
Just put NN dot sigmoid in parentheses.
Great. Yeah, so there you go. We've established the different layers of my model. Currently, we have 3 linear layers, and we have 1 activation layer. And I see a question from Len. Let's hear it, Len.
I understand that you're having 3 layers, and that's why you chose the 9774441. Is there a process that you go through, or is this an experience kind of thing where you just know what numbers to cut down to?
Yeah, that's a great question. So when it comes down to it, the 2 things that we need to ensure are actually happening is that I place in 9 and that I'm outputting 1. If I wanted to make this a 2-layer neural network, I could, where I would go from 9 probably to 4 and then from 4 to 1. As far as how I define these numbers, it's just trial and error. I try to go with the 2/3 rule, right? So if
Okay, you
I,
did say 2. Okay, got it.
yeah, so that's what I try to do.
What is it? What is the 2/3 rule? Because I don't remember that one. I know you said it, but I don't remember what it actually is.
Yeah, so if I have 9, then ideally I would go with 6, right? And
Okay.
then 6 would cut down to 4, and then 4 would cut down to 1.
Okay, and then you always round up, or and I know that I'm getting into like nitty gritty here. I understand, but like in general, all right, I'm just talking about in general. Would you round up or down?
I think up would be the right call in that case.
Okay, thank you.
Of course. All right. Oh, Mikkel, let's hear it.
What determines how many layers you use?
Yeah, as far as how many layers you utilize, there is a mathematical function that you could use to kind of determine this, but it's honestly just come down to performance, how much data it is that you're accounting for, and how accurate your model is. So if you try to put it through the training process and you put it through the training process over and over again, and it's still just missing by a long mark, and you know for sure you have the correct learning rate and momentum and you have everything else correctly, then maybe it just needs an additional layer to be able to make better connections. Does that answer your question, Mikhail?
Okay.
All right. So now moving on to the forward pass. The forward pass is utilized to take in our neurons, right, and actually pass them through all of these layers, all the way through the activation function. So this X is representing our input tensor. So let me go ahead and change that to input tensor. And now let's define how this would all get passed. All right, so let's say output 1, and this would be where we pass in the input tensor through our first linear. This would be output 2, where we place the value of output 1 through our second linear layer. Finally, we repeat the process. We go to output 3, which takes in the output of 2 into our third linear layer. And then we say, this is our outcome, if I could spell, which puts in our final output from linear layer 3 through the activation function of sigmoid. And we return the outcome. And that is the forward pass, right? So we could write it this way so that it's a little bit more visually appealing. The convention that you will see if you try to look at documentation will look almost exactly the same. It'll ask for the self, the forward pass, but rather than doing output 1 and describing that it's going down the flow, you'll just see X is equal to self.linear 1 that takes in X. Then you see X is equal to linear 2 that takes in X. Then linear 3. And then you'll see X. And you would return the value of X, right? It's the same thing. You're just doing variable, or you're just overriding the value of the variable, but you're still just feeding the input tensor through each layer, grabbing that output from the activation function and returning it. You're just doing variable reassignment. And I saw a hand go up. Did I answer your question? I'm not sure whose hand that was.
Yeah, you did. Thank you.
Okay, awesome. Gary?
Yeah, can you repeat what X is doing? I'm sorry.
Yeah, definitely. So X is still just the input tensor, right? It's a variable that you're just overriding. So when first it's the input tensor, when you feed it through that linear function, it gets stored into the variable of output 1. Well, now it's just the variable X, right? So its
Okay.
value changed into the value of output 1. And then so on all the way into the activation function.
All right, thank you.
Of course. All right. So we build our model. It has the correct number of linear, well, not correct, but it has a number of linear layers that we hope will give us a good prediction. All right, we're using the correct with a correct activation layer, because for binary models, sigmoid is the expected activation layer. And we've declared our forward pass to be able to pass in tensors. So let's go ahead and make our model here be equal to the instance of a binary model. And let's try to create a tensor. All right, for no values, I'm just going to go ahead and place a 0 in there. Let's start off with one that has no values. Oh, that one also has a no value. Yep. We'll just put a 0 for no values. All right, so let me grab that and put it right here. And click input tensor. And let's call this a dummy input tensor. We're going to make that equal to tensor. Oh, of course. All right, so there's our dummy input tensor. We have it of the correct size and shape. Oh. And let's actually make sure that that's the case. Let's print the dummy input tensor size. And if we run it, we see that this is a tensor of size 9, right? Which is what we want. We want 9 neurons that we're passing into our initial layer. Great. Well, let's make our prediction be equal to our model that takes in our dummy input tensor. And let's print our prediction. All right, so there you go. Our model accepted this tensor. Excuse me. It fed it through our neural network that we drew out here. Our weights and biases were applied. And then our sigmoid function squeezed it between 0 and 1 and gave us an output. So according to my model, as of right now, this is definitely something that should be drinkable. Now, if we take a look at our data here, we see that our model is wrong, right? And it's wrong by a long shot. So we'll go through fixing that as we start training our model. That's what we want, right? We want to get our model to the point where it can work with this data, take in one line at a time, feed it through the neural network, and then we could tell it, hey, you were right, maintain these weights and biases, or you were wrong. I need you to go work backwards and update these weights and biases to give me this input. All right. Does anyone have any questions up to this point? Okay, great. All right, so far all of this should be review material, right? This is what we did. We covered last week. We took in our tensors, we talked about data, and we talked about building our models, either utilizing NN sequential or by building an actual NN module class. We talked about the benefits of each and decided that the NN module class is actually more beneficial than NN sequential, since utilizing it with a module gives us much more control over how data is being fed through a neural network in the forward pass. Whereas in NN sequential, we have no control at all. We just define each layer, define an activation function, and the sequential function takes care of the forward pass for us. Okay, great. Well, now let's actually start covering the topic of today, where we're going to start working with data. Now, when it comes to data, we talked about a couple of things that we want to ensure are happening, right? We want to ensure that there's some sort of standard so that all of our data is formalized or looks somewhat the same. And we talked about normalization as well. So there's a couple of things. There you go. This is called scaling and normalization, right? When it comes to your data, I like to imagine data as a consistent flow, right? Oh, let me go ahead and make that extra large here. Let me zoom in a bit. All right, so I like to imagine my data to be a consistent flow, where it's a bunch of zeros and ones, and maybe every now and then we have a spike kind of above. Well, this is all good because it fits within my lines, right, of normalization. The data flow that is being fed into the model is between some sort of left and right lateral limit, right? Sure, we have some spikes that may reach those left and right lateral limits, but they're still within, right? Well, where there comes a problem is when the data continues, a left and right lateral limit has been established, and then all of a sudden, we get a massive spike, right? Where our data just goes completely out one way and then comes back and falls back between our left and right lateral limits. Now, this may not be a big deal for us as people because we could easily just say, oh, well, we just won't take that value into consideration, whatever that was. We'll take that sample and take it out of the data set. Well, when we're talking about data, we can't just remove something out of the data set, right? And we need to find either a smart way to grab this data sample and say, well, likely this point here is inaccurate, or maybe this is a special case that we don't necessarily need to account for. So we need to find a way to grab this pattern that we have here and correct it so that our model knows, oh, hello. So that our model knows that when this happens, rather than going all the way up there, we're going to correct the flow of data and bring it back towards some sort of either middle, min, or max, right? So there's a couple of different options there. Whenever this happens or a spike of data occurs, or maybe there's a completely no value, there's an absence of data, you could handle it where you could either choose the max of the consistency of the data, You could choose the minimum of the consistency of the data, or even better, you could choose the mean, right, of where your data is falling. Those are just three separate ways to implement each one of them. We're not going to go too far into how each one of them is applied. Here, what we're going to be utilizing shortly will be the mean, where when we encountered values that are not falling within standard, we're going to utilize the mean to bring the data back in between our left and right lateral limits. All right. Does anyone have any questions over that so far? Let's hear it, Len.
I can just consider the mean the average of what is happening so far, right? In like, it's just another way of saying the average. I'm not saying it is the exact average, but it's another way of thinking about an average of what's coming in and out.
It's a way of thinking about it. Yes, mathematically, it's not the way
Yeah.
it's working, but yes.
No,
it is a
I
way
get
of
that. I
thinking
just
about it.
having the word mean in my head right now. I'd rather just, yeah, never mind. It's a me thing.
Awesome. Joseph?
So if you collect enough data, there's always going to be some level of variance or outliers, like Eric was saying. But doesn't altering those outliers, like you're purposely manipulating the data to like fit the outcome of the model. Isn't that like a bias, like manipulating the data, like you're altering the variance so that it fits the model? Isn't that like shaping the data so that you get the outcome that you want? Don't you want to like actually represent the variance?
Yeah, that's definitely a good point, right? And when it comes to training the model, it's not that we don't want to represent these variants, right? Currently, right now, what we're looking at is data for training, right? I don't necessarily want my model to be trained on outliers or to consider outliers, because then it'll make the training harder or inefficient for my model to actually learn, right? I want to train it on good, proper data. And from that good and proper data, it will be able to accept these outliers and provide good predictions. Does that make sense, Joseph?
Yeah, thank you.
Of course. Erica?
I just wanted to add to that by saying that outliers like significantly deviate from the rest of the data. So because of that, they can skew the data way to the right or to the left, meaning that when you are running the model or when you're running the neural network, it's going to skew the results too. So you do want that since it is like these are one-off cases. This is where data preprocessing comes in, where your analysis comes in, and if you do want to leave or not the outlier in consider what it can do to the model afterwards. But in general, you do want to remove outliers.
Awesome. All right. Thank you for adding that, Erica. So that's going to be the reason behind utilizing our standardization and normalization here. But the next thing that I want to talk about is breaking up our data, right? And I want to quickly touch on this so that when we start writing code, we understand the why we're doing deep breaking up of data, right? Well, let's think about us ourselves first. If I were teaching the same exact material over and over again, right? And we were always getting evaluated on the same thing. So let's say our SQL assessment, we just finished our SQL assessment. If I were teaching the same exact lectures over and over, word for word, letter by letter, or each character of code at exactly the same time, over and over again, and everybody was taking the same exact assessment over and over again, right? And at the end of every iteration, we also did a review of that assessment where we by hand went through each query and evaluated how we come up with the correct answer. Now, how long will it take before everybody starts passing that assessment? Probably not very long, right? But not for the correct reasons. So people could start passing that assessment for the simple fact that they've memorized the answers, right? Every time we did the review, well, after seeing the review done 7 or 8 times, I've probably memorized some of these answers, especially if it's only 10 queries. If I'm receiving the same exact information over and over again, we all know that just hearing something the same exact way in the same exact manner isn't necessarily going to make the light bulb click, right? Or it's not going to make us actually retain information. Instead, what our model would do is memorize answers. So when we talk about data, let's say this is our body of data, right? Our body of data should get broken up. So one, we should have a testing data that is typically around 80% of your data, or excuse me, our training data that's typically around 80%. So let me go ahead and put that in there. And then we should have our testing data, where our testing data is typically around the leftover 20%. Right? Now, let's take it a step further. We have our training data that we're going to train our model with. We're going to say, hey, I want you to utilize this data to actually learn. I want you to make a prediction, and every time that prediction is wrong, I want you to adjust the model and fix yourself. All right, so it does that. We're starting to get some good predictions. Our loss function is pretty minute, and we have a good level of accuracy. Well, now we put it through our testing, and then it's able to pass our test. Well, that's great. How do we ensure that our model didn't just memorize this data, right? Well, you don't just want to feed it one set of testing or one set of training data in itself. Instead, you want to have different batches of data that your model will train in. Right? So we would take in our master data file, and from our master data file, we would create. This is kind of at random, right? It's really, oh, hello. Okay. It really depends on how much data you have available to create for batches. But in general, I like to stick with the number 4. If I can make 4 batches, then great. But again, it depends on the amount of data that you have. All right, so I would take my master data file, and I would break it up. I would have 4 separate batches. That ensures I'm teaching my model in 4 separate approaches, right? This is the same thing as having 4 separate instructors give the lessons over SQL, teaching, hey, this is how you utilize SQL queries. And then I have 4 separate assessments, ensuring that my model is actually retaining the information and that it's making accurate predictions, right? So that's why we break up our data. Does anyone have any questions over training sets, testing sets, and breaking up data? All right, I see a couple of good links already being dropped by Erica on the chat. Thank you. And let's see. Okay, great. It doesn't look like there are any questions. We have gone on for quite a while, and we're about to dive into some coding. So before we dive into some coding, let's go ahead and take an 18-minute break, try to freshen up, and then we'll come back and dive into coding at 10 o'clock. So thank you so much, everyone, and enjoy your break. All right, everyone, welcome back. So we have our data here from the water potability. We've talked about how we would break up our data. We talked about normalization and standardization. And we have also talked about what our binary model looks like. Just in code, we created a dummy tensor that is essentially just the first row of data. Currently, we haven't done any sort of standardization or normalization to that first row. It was the copy of paste. We printed the size so we could ensure that it was, in fact, 9 neurons that we're feeding into our model. And then we made a prediction by feeding it into the forward pass of our model, where this tensor was inserted, manipulated, and turned into one single output tensor. And that output tensor evaluated to 1, which is equal to true. All right. That's all we have as of code right now. But now let's go ahead and start actually working with our data. Now, in order to work with my data, I have a CSV file. Well, what we're used to is doing something like import CSV and then writing our whole with open function, right? Where we specify, hey, within this directory inside of resources, there is a water potability.csv file. I want you to read it and ask CSV file. And then we utilize something like CSV, or maybe we do reader is equal to CSV dot dict reader, and we pass in the CSV file. And then finally, we do our whole for row in reader print row. Right, and I'm not actually going to do the whole thing because we know that that's going to be a considerable amount of rows. I think we have all the way up to the thousands here. Let's see. Yeah, so we have 3,000 rows. So that's a considerable amount of data. A lot of edge cases that we need to account for. If I wanted to write some logic to just identify where null values are existing, I mean, that would be a function that would have to be activated for each one of these rows, right? So this is, although Python offers us a pretty user-friendly way to interact with CSV files, it's definitely not the most efficient, all right? So let's go ahead and let me see if I could do something like slicing here. I wonder if that will work. No, it doesn't like that. All right. So this isn't good. I'm not actually going to execute this. It would just be a considerable amount of print statements. So let's start talking about how we would actually work with some data files, right? Well, when it comes to data and manipulating data or just interacting with data, we would actually utilize something named Pandas, because Pandas would create a special data structure for us named data frames. And data frames are just much more friendlier and nicer to work with, but we'll see that here. Let's go ahead and start off by activating my virtual environment if you don't already have it activated. So currently mine is within environments at .lmenv/bin/activate. There you go. I've activated my virtual environment through my terminal. Now I'm going to go ahead and pip install pandas. So there we can see that pandas is being installed. It looks like I've installed it before, so it has some requirements that are already satisfied, and then it has some cache data as well. And now by downloading pandas, I can create this data frame from my CSV file. And it's actually a lot easier to work with pandas for reading this information. So I'm going to go ahead and import pandas. And I'm going to import that as PD just for simplicity so that I could write it quickly. I don't need this as, I could just utilize pandas, but I'm making an alias so that I can quickly identify that package. Then I'm just going to say data. And for that variable, I'm going to utilize this read CSV function. And notice there's a couple of them, right? There's this read CSV. I can read Excel. There's tables. I don't even know what stata is. You can even grab data from JSON queries. There's quite a bit of different reading capabilities that Pandas is giving us. Well, let's go ahead and do read CSV. And the only thing we're going to specify to this path is where our CSV file is located. Well, it's located in resources and it's named water potability. I don't even know if I'm saying that correctly. .csv. Is it potability or potability? Who knows?
Tomato,
All
tomato.
right. And now let's go ahead and print our data so we could see it. Well, when I execute this, we'll see it's taking a little bit of a while. It's not happening because of Pandas itself. It's because it's interacting with my virtual environment for the first time to grab Pandas. After this, it'll be much faster as far as execution goes. There you go. We were able to import Pandas. And when I ran, hey, here's my data, I want you to print data. Look at how my data is being printed. I have my headers on the top. And then I have my numbers of each individual row on the left-hand side. And it's just much nicer format, much more nicely formatted, right? If we wanted to mimic some sort of similar information here, we would probably iterate through and we would get some sort of dictionary where the value would be the header, and then we would see each corresponding key as the value, or excuse me, each value as the input through the CSV file. And then we would probably have to add the index in there as well, right, to try to mimic some sort of output here. But notice it's giving us the headers here on this first row, and then I get this backward slash. Well, this backward slash is because the table continues, right? So this is showing me both the head of the file, which just shows me all the way up to row 4. And then it's also showing me the tail of the file, which it tells me goes all the way to 3,275. And here you go. It also gives me a very quick summarization as far as the dimensions of my table. It's telling me, hey, you have a total of 3,276 rows. Just like everything in programming, we start counting by 0. That's why our final index is 3,275. And it tells me you have 10 separate columns. All right. And Erica, I see you have a question or maybe something you would like to add.
Oh, if you want to see like it super nicely portrayed data dot head parentheses makes it look amazing.
Yeah, awesome. We're definitely about to go into those methods as well. All right. So now, just like Erica mentioned, let's take a look at what data.head looks like, right? Because like I mentioned, this is giving me both the head and the tail. When I execute, now I can see only the head, right? If I execute tail, it would only show me the tail as well. Well, what else does Pandas bring in as far as this data frame structure, right? Why is it important that I have these headers here? And what things can I do? Oh, excuse me. You're saying to remove the print statement here so that we could actually see it? I'm gonna try it out. Oh, look at that. Remove the print statement and it gives it to us in a strict table here down below. Look at that. Thank you so much, Erica. Oh, all right. It's not letting me scroll through, but there you go. All right. And if we do head, just to demonstrate that, and we run it, there's the head of our table. There you go. Nice. All right. Well, just like I mentioned, we have our headers. What can we do with those headers, or why is that important? Well, if I had a column or a specific data or operation that I had to run on only one column of data, I would need a way to only grab that one column. Now think about our previous way, right? Where we imported CSV. We would have to do something like column is equal to, and then for every row, we would say, all right, well, now I want a column to append the data of row where I have pH. Right, and that's how I would grab the column for pH. Well, that's one way to do it. I would have to iterate through the entire structure, build this one specific memory space for column, and then be able to print it. But data frame doesn't actually work like that. Once the data frame is built, it's done. Everything else is already accessible to me without having to iterate through the entirety of all those different dictionaries or rows all over again. So let's grab something by a header, right? If I wanted to grab something by a header, well, I could just specify, hey, I want pH. And I could print this here so that we could see this column. And there we could see all of the output for pH. It tells me, hey, here's the pH starting from row 0 all the way to row 3275. Here is the data type that we are interacting with. It looks like all of them are floating points 64. And that's important because all of my tensors need to be floating points. And it tells me that the column name is pH. Great. Well, let's take a look at other headers, right? Let's say I wanted to take a look at something like, oh man. Ooh. All right, let's hear it, Brandon.
I understand that the tensors need to be in floating points, but does the decimal precision matter?
Yeah, that's a great question. So when it comes to decimal precision, it definitely does matter. The more accurate, the better. So I believe the other type is float 32, and then there's float 64. What we definitely prefer is float 64. It will accept float 32 and feed it through the neural network, but we would prefer to have something like float 64. Does that answer your question?
Yes, thank you.
Of course. Boom. All right. So there we can see how easily we could grab columns. What about rows of information, right? How could I do that? Well, if I just wanted to see my first row, I could just call the ilog function and say, well, I want rows 0 and run that. And it gives me all of my columns on the left-hand side with the rows corresponding, right? If I wanted to conduct something in a specific row, let's say row 3120, right? And I execute that, well, it would give me immediately the values, like it's giving me direct access for this location, right? I could also do something like slicing. I can say, hey, I want from rows 5 all the way to rows 10. And it gives me a table again. And now I'm curious if I take off that print statement, if it will also give me that handy dandy statement that Erica showed me. And there you go. Right. So there you go. I take off that print statement and I'm able to slice the independent number of rows that I need to conduct some sort of operation on. I see a question here from Brandon.
Yeah, so when you tried slicing earlier with CSV Reader, so Pandas is doing something different that allows us to slice, whereas CSV Reader we couldn't.
Yeah, so Pandas under the hood is essentially building a series of dictionaries and lists, right? Which is why we always have direct access to information because it's just building dictionaries under the hood. Does that answer your question, Brandon?
Yes, thank you.
Of course. All right. Okay. So now that we've talked a little bit about the capabilities that Pandas brings in, let's talk about our first problem here. All right, let's say we wanted all of our data from rows 0 through 10. There's just 10 rows of data. And in 10 rows of data, we can see that we already have quite a bit of null values, right? So here we have a not a number. That's what NaN stands for not a number. That should be familiar from, I think, just JavaScript, or is that C#? I'm pretty sure we see it in JavaScript as well. This NaN functionality, right? So it's telling us, hey, this is not a number, it's a null value. Well, if I try to feed something like a null value through my neural network, so if I try to go up here to my neural network, and instead of passing in a 0, try to pass in something like none, right? Well, when I try to execute this neural network, it tells me, hey, this doesn't work for me. You're trying to tell me to represent none as one of my neurons. So I need to find a way to handle all of these null values and replace them with something else in my data. Well, first, let's confirm that we do have null values, right? Because right now they're within rows 0 and 10. But what if I had something where there's some null values hidden in row 2000, 2000 and something, etc., right? Well, I don't want to run my program and then find out that that specific null value exists way down the road. I want to know right off the bat. How do I know that? Well, let's see. I think, right, Pandas would have some way for us to identify that easily. So we're going to actually run the data is null function. Let's run that. Well, for data is null, we can see that it goes through the entire data file and it brings back for each statement, hey, is this a null value or is it not? If it is, it returns true. If it's not, it returns false. Okay, somewhat useful. Again, if my information was hidden in between my head and my tail, how could I identify that there are some null values? Well, I would just add the sum. And by adding the sum, now we get a very clear, hey, in pH, you have 491 null values. In sulfate, there's 781 instances of null values. And in whatever this is, I'm not going to attempt to say that, there's 162 values. And I keep seeing Erica trying to tell me to take off my print statements because Pandas is fantastic. So let me take off my print statements and there you go. All right. So it's able to create this table that very easily tells me in integers how many instances of null I have throughout my data table. This is great. I know that there are null values within my data table now, and I know where they are occurring. Right? So later on when I'm training my model, if I'm seeing that there's some sort of issue and it's coming back to the neuron that's representing pH, it's likely because of the way that I handled my null values. Right? And we'll go further into that once we get into the training process. Oh, I see a hand up. Go ahead, Erica.
I feel like we're gonna go into imputation afterwards, but we can also, from the data is null sum, we can calculate the percentage of data that might be null and then see if it requires imputation or not.
Awesome. Yeah, I don't think we are going to cover that just because of time, but definitely a good thing to look into. Thank you so much, Erica. All right. So
sorry,
now,
I'm super passionate about this stuff. I'm sorry.
no problem at all. It's always welcomed. All right. So now that we have this information, we understand how many null values we have in our data. We have a good way of representing it. But how do I fix it, right? How do I make sure that my data is clean? Well, what I'm going to do is I'm going to take all of these null values and I'm going to replace them by the mean, just like we talked about down here. right? Well, I have my null values. I can't have them just go unrepresented. So I'm going to take the mean of pH and make that essentially the filler for my null values. And same thing for sulfate and for, I'm not sure what that is. I'm just going to go with trihal. All right. So let's take a look at that. I'm going to go ahead and run data pH here. And that should give me some information. And I'm going to do it in a separate block, actually. Data pH. And if I'm correct, that should bring me my data for pH, right? And let's actually just do dot iloc and do row 0. All right, so there's row 0. We see that pH has a null value. Well, let's see what happens when we run the following function. I'm going to grab my data. What I'm going to do is I'm going to fill my null values. And I'm going to fill them with data dot mean. Then I'm just going to pass in the in place equals true. Everything's happening under the hood. All right, it's going to grab specifically the pH and do the mean. I understand that I'm passing data dot mean, and you may think that that's referencing to the entire body of data, but that's not the case. Pandas is handling it all under the hood. And now when I run it, oh, excuse me, let me go ahead and wrap both these up in a print statement. I know I don't necessarily need the secondary one, but I want to view both of them. Oh, I need to restart my kernel. I apologize, everyone. All right, so there's my first iloc statement where I see, hey, this is not a number. And here's my secondary iloc statement. Now, instead of telling me, hey, this is not a number, it's giving me the mean for pH of 7.08. All right, and I see a question. Go ahead, Eric.
So I would assume that would work if you have more than one null value. So if you had like, I don't know, sulfates were also not a number, it would also replace that with the mean.
Right, so this is happening to the entire data structure. So now, if I do data dot is null dot sum, and I execute this, I would get 0. Because now there is no null values inside of my data table. All of them have been replaced and filled in by the mean of their independent column.
Okay, thanks.
Of course. All right. So now I've cleaned up my data. Oh, another, let's hear it, Gary.
Oh, my bad. Yeah. Where is it that actually getting filled again? Can you go back up and show where it did the? Is it the data dot ilog? No, that gives you the row. Where is it actually putting in the mean value?
Here, that's where it's getting filled. So it grabs all of my null values with fill in A, and then it puts in the mean.
I see. I got you. My bad. Thank you.
No problem at all. All right. Okay. I heard a pop. Where'd that pop go?
That was me. I was
Oh,
putting. But gotcha.
okay. All right. So now we've gone a little bit through the process of making sure that our information is, somewhat within standards, right? We've handled for null values, which kind of takes care of this spike here, but not really, right? Well, handling null values isn't the same thing as taking care of this spike, right? What I'm taking care of is the absence of data. So now there is no absence of data. The next part that we're going to do is taking care of spikes like these, of ensuring that all of our data is following between our left and right lateral limits. And I keep using left and right lateral limits for those of you who are mortarmen or infantrymen. I'm sure we have some, you have some relationship to those. Or I'm not sure if we use them anywhere else in the infantry. Well, pretty much all of the infantry uses them. Does air use them? You guys probably do. Anybody here a pilot? All right, moving forward then. So we have scale and normalization for our data. Well, let's talk about our data. We want to break this up, right? I have my 9 features, and then I have my label, which is my truth, right? So these are the features that I'm going to be utilizing to train my model, and this is my truth. So I need to separate those now moving forward, right? So I'm going to specify, hey, my features are everything from data with the exception of the column portability. And then I'm going to pass in this axis 1, which is just a required statement. I'm just basically saying, hey, don't try to nest anything. Stay within your same column. Don't worry about it. We're just dropping this one column. All right. And I'm not going to print. Actually, we could probably just do features here and see how that looks. So now we can see that features has been created and it has our 9 attributes all the way up to turbidity. Cool. But it does not have potability. All right. So this is great. I now have my features. Well, what about my target or my label? Well, my labels are just essentially the entire potability column. All right, so there you go. I separated my data to where I have all of my features along with their corresponding labels for each row. All right. Does anyone have any questions up to this point before we continue moving forward? Let's hear it, Mikhail.
What was the access equal 1? What does that do?
Yeah, the access equal 1 is it's a required argument for access. We need to tell data or the new creation because we're essentially creating a new data frame. If this needs to be nested inside of some sort of parent. In this case, we don't, so we just pass in the access equal 1 saying we're just dropping a table, everything else remains the same. Does that make sense, Mikhail? All right, I saw the head nods. Momo?
Yeah, I have a question, please. Why we drop this portability?
Yeah, so we're dropping potability because we want to start separating our features, which is what we're going to be feeding through our neural network, and our labels, which is going to tell our neural network, this is what you should be evaluating to. This should be a 1. Because this fails, you need to go back and fix your weights and biases. Right? So I need them to be separated from one another because I'm not feeding the potability column through my neural network. I'm only feeding the features through the neural network. Does that answer your question, Momo?
Yeah, so that means we're gonna feed the 9 properties or the 9 features like with the same mean?
Exactly. Yes, we're gonna feed the 9 features through the neural network.
Oh, okay. Thank you.
Of course. All right, so now that we have it separated, how do we actually standardize our features so that everything is falling within some sort of standard and it's normalized, right? Well, we could go through it and do some sort of crazy math to try to flatten everything and ensure that everything is working correctly. But luckily, somebody has developed a tool for us to utilize that will allow us to standardize and format our data much more efficiently without a lot of us manipulating the data. All right, so we're going to install yet another library called scikit-learn. Gonna go ahead and pip install scikit-learn. All right, so there we see it installing. it was successful. So now I have scikit-learn, and I'm going to go ahead and share that here on the X-ray channels. Oh, excuse me, the X-ray questions channel, so that we all have it available as well. And what this is going to do is it's just another data library or package extension, whichever you want to utilize to reference it. And it gives me some more tools, just like PyTorch gives me tools to actually work with data and transform it into something that's standard. So I'm going to open up another code block here. And now I'm going to standardize my data. Now, when I go into standardizing my data, I'm going to reference from sklearn or sklearn dot preprocessing. I'm going to import standard scalar. So just like the name says, we're going to standardize our data, right? So now I can make this a variable where I say scalar is equal to standardize, a standard scalar. This is a class. We can identify that that is a class from the capital S. So now I'm creating an instance of the standardized class or the standard scalar class and saving it into a variable named scalar. So now I can say, hey, scaled features is just the scalar of fit transform method, right? The fit transform is a method that belongs to the standard scalar class, and it takes in a data frame. So I'm going to pass in the data frame of features. This is going to standardize my data, and then I'm going to get it back in a standard scale. So now let's go ahead and run scaled features.head. It's probably because of the .head attribute. Yep, because now it's a numpy array. All right. All right. So now let me print our features at index 0. There we go. All right, so now we can see first we're grabbing through iloc. This is a data frame, right? I'm grabbing my first row of features. So here we can see the corresponding values for my pH, the hardness, some solids. Each one of the 9 features are being represented here. But after I transform them and standardize them, we can see that their values have completely changed to be really small numbers, right? So now they have been standardized so that our neural network can work with them to evaluate and make consistent, accurate predictions as to whether this data would produce a potable or non-potable water source, right? It takes in the features. It's going to say, hey, this gives me an output of 0.3, and that means that it's less than 0.5, so this is not drinkable water, right? I have now standardized my data. And it's not a small change, as you can all see. For example, solids went from 20,791 point whatever, and that changed to a -1 with some sort of irregular expression at the end, right? So we have standardized our data. Everything has been flattened, and now we have data that we can actually work with. All right. Before I continue moving forward into the breaking up of information, does anyone have any questions over what we just did. Let's hear it, Mo.
Yeah, I'm sorry. Just the standardization, the standardize the data. I didn't understand the idea of the standardization.
Are you asking like pretty much like why are we doing this?
No, I know the math. I know how to do it as a logic, but yeah, what the meaning of standardization again? One more time.
Got it. So standardization and normalization. We're essentially making sure that our data is clean, that it's been swept, that we don't have any sort of missing values in our data stream that we've drew out here, right? And that all of our values are not falling out of our left and right lateral limits. We're making sure we're declaring a clean data stream between these two arrows. Does that make sense, Mama?
Ah, okay, I got it. I got it. So that the step, yeah, okay. Thank you. Cleaning data.
Yeah.
Thank you.
All right. If there aren't any other questions, now we have our data to be able to work with and actually train a model, which we won't be going into today. But now that we have this data that we've created, there's two things that I want to point out. One, this is a data frame. This is happening from features.ilog. Scaled features, which is our data after it's been normalized and standardized, is returning back a NumPy array. We haven't talked about NumPy yet. Well, a NumPy array is essentially just a tensor, right? Tensors were inspired from NumPy arrays, and excuse me, and PyTorch is actually running a lot of NumPy and Pandas functions under the hood and just trying to simplify their functionality for us as far as syntax. So at this point, we're actually manipulating the equivalent of a tensor, right? Well, now that we have this massive list of tensors, how do we go about separating this data? All right. So there's a couple of ways, or, we think about it, there's probably a couple of ways of creating these batches of data. In this case, we're going to be creating two batches of test and training data. Now, how can I do this? Well, earlier today, and this is kind of going into statistics and data analysis, right? Earlier today, when we talked about how to handle inputs that were outside our left and right lateral limits, I believe Joseph brought up a point about being biased, right? Well, how do you ensure that these two groups or two samples that we're utilizing to collect data and train our model aren't biased? Well, we could do something like random selection, right? Because if I specify selection depending on some sort of attribute, I'm definitely going to end up with biased data. Now, instead of saying, oh, well, if the pH exists, then we'll put it in batch 1. And if the pH is the mean that we calculated, then we'll put it in batch 2. That would create biased batches or biased samples that we would put through our neural network. Instead, we're going to use something kind of like a randomized iterator, right? At random, I will choose which batches or which parts of my data will go into each individual batch. And at random, I will choose which ones will be utilized for training and which ones will be utilized for testing. Now, there's the whole question of, do we want duplicates on each batch? Do we want duplicates not only on each batch, but do we want duplicates inside of training or testing data? Not all of them, but maybe one or two. There's a lot of things to consider as far as creating good sample data or good samples that we can actually put through our neural network. And thankfully, someone has already came up with a really simple function to be able to split all of our data and create this 80-20 ratio, rather than us having to write a function that will randomize this data. After randomizing it, separating it into some sort of batch, it would be a whole mess if we try to do it ourselves, utilizing pure Python, right? So instead, I want to break up my data. So here we'll go into breaking up training and, or let's just call it batches. So now I'm going to break up my batches. My batches should ensure that I have 2 batches total. Each batch should have where 80% is for training and where 20% is for testing. All right, so there's my 2 batches, and those are my requirements. Oh, how do I make that happen? Again, oh, hello. Let me add a code block here. There we go. All right. Well, SQL Learn has gave us another function that we can utilize. sklearn, there you go, has gave us another function that we can utilize to make this split happen. And it's called a train test split. All right. Nothing too complicated or crazy about the name. And the name does exactly what the function does exactly what it's called. All right. It's going to split our data and create training and testing batches. So now let's go ahead and run this function. Let's say batches is equal to train test split. This train test split is going to take in 1, my numpy arrays, which is just my scaled features. Then it wants the targets. It wants to know, hey, what are the answers? Well, we stored that inside of a variable named labels, and they correspond by index, right? Index 0 of my scaled features would output index 0 of my labels. And then it wants to know the test size. Well, what is the test size? We talked about our test size being 20%. So how do I specify that here? Well, in decimals, 20% is 0.2, right? So it's going to assume, hey, if 20% is being utilized for testing data, then 80% will be utilized to create, excuse me, then 80% would be utilized to create training data. And then finally, it needs a random state. Now that random state, just like I mentioned, we want to create some sort of randomized iterator saying how often should things be randomized, or how big should our random batches be. And in this case, I'm choosing 42. It doesn't necessarily have to be 42. I recommend that you utilize a larger number rather than a smaller one, and that it is an even number, because it's going to try to create pairs, right? When you feed it through the model, it's going to feed it in pairs. It's going to make 2 predictions, and out of those 2 predictions, it will then come up with some sort of, this is my error margin, and this is how I can fix myself or update the model's weights and biases to be more accurate. So you want an even number, right? I could go something as low as 2. I could go with something as low as 4. But let's say in the random case that my data ends in an odd number, and I only have batches of 2. Well, that last statement, or that very last row of data, wouldn't have a way to get paired with anyone else. Whereas if I make it in a larger number, it's going to identify, hey, this one is by itself. We're going to duplicate one of the other partners or rows so that it does have a partner what's getting fed to the neural network. That's all that random state is doing, right? We're randomly selecting 42 rows at a time to be placed inside of a batch. And this is if possible, right? Well, now currently I have it named as batches. But that's definitely not something that we want. Let's go ahead and take a look at what would happen if I fed it and try to print batches. Labels is not defined. Labels is defined. Let me make sure. Okay, labels is defined. We run that. All right, there you go. So now if I try to feed it this way and I put it through batches, we get back a array of numpy arrays. And this is just an array, which we can see has one. It's a ridiculous amount of nesting. Essentially, I'm getting back four separate batches here. So I need to specify how they fall in. And the easiest way to specify how they fall in, well, I can say batch 0. And there you go. That would give me batch 0, which we know this would be technically batch 1. And I could say training data, which is what gets returned in batch 0. And I could just print batch 1. Right, and that would work perfectly fine. And I know that batch 1 testing data is returned inside of index 1 for batches. All right, how do I know this? It's within the documentation. I could leave a link to it or send out a link to it. But note that that's what's going on here, right? It's returning 4 separate arrays. It's returning one array with 4 separate numpy arrays inside of them. So currently what this is returning, this function is returning one massive array with 4 separate ones inside. I know that index 0 would be a training. Index 1 would be a testing. Index 2 would be training again. And index 3 would be testing. So here's the information that's coming back. Great. Well, there's a more efficient way of grabbing information than doing it here by index. And we saw it a lot in JavaScript, especially when we were interacting with useState and changing props, which is just spread operators, right? Rather than writing everything one by one, I can just destructure information and grab each training and testing array. So instead, I'm going to say, hey, this is going to be training 1, testing 1. I'm going to grab training 2 and make testing 2. This will still execute correctly. And now I have my 2 batches. Right, 2 batches were created where training has 80% of the batch size and testing has 20% of that batch size. And that is how we separate data. Does anyone have any questions up to this point? Let's hear it, Erica.
In our classes, we were told to normalize after splitting training and testing so that we can then test if our results, if our predictions reproduce in unseen data. So that it doesn't modify the test data too. And you can more reliably test if it reproduces the results.
I see. So you're saying do the split, that you were taught to do the split first and then do the
Yes.
standardization.
Yes,
Okay.
and only on training data. So that like you can see, you can test if it reproduces.
Okay, great. Yeah. Momo?
Yes, sir. So that means if I want to make 4 batch, I'm just destruct this to training 1, testing 1, blah, 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 until training 3, training 4?
No. If I try to add any more arguments, it would give me an error because this train test split only returns it only returns 4 by default, but you can see that it gives me the option that I can specify, right? So test size, train size. There's a different function or an extra parameter, I can't remember off the top of my head, that you can pass into this to specify a different number of batches.
So that's the default for 2 batches, right? This function.
Correct.
Okay, thank you.
Of course.
Yeah, thank you.
All right. So now we have this. We have all of our tensors, or excuse me, all of our numpy arrays. But now let's turn them into tensors. All right, let's turn them into tensors and let's make sure that they are of the correct type. So let's go ahead and say this is training 1 tensor. And I'm going to utilize my tensor function here. And what I'm going to pass is training 1 as my argument. And I'm going to specify the data type. I see here on demos and notes that it says float 32. I'm going to go ahead and try this out with float 64. Oh, look at that. Yeah, so it does give me float 64. Let me see what that does. I probably experimented with this and ran into an error, but I want to make sure that this is correct. All right, this is going to create my tensor. Now, if I finally put it as my output of my training tensor, and I run this, we can see back, we get 1 tensor with 9 neurons, right? And it comes back with float 64. Awesome. So there you go. I have my tensors. How do I go ahead and feed this through my actual model? I already have my model initialized up above. So I can say, hey, prediction for, let's just say prediction for now. And I can call my model and pass in my training tensor. And there's my error, which is mat1 and mat2 should, but got double in float. So it looks like there's our issue where I try to pass in float 64. And what it's actually looking for is float 32. And there you go. So I was wrong earlier. I think who was it asked that question? It was Brandon. I said that we would want float 64. We actually want float 32 because they're interpreted differently, where float 64 is a double and float 32 is interpreted as a float. Does that answer your question? Or, well, it's not really a question, but making sure that that correction is in there. All right. So now let's go ahead and print our prediction. And when we print our prediction, now we're getting 0.52 for my very first tensor. And let me actually go ahead and do that. Let's go with index 0 so that we're only feeding the first one. All right, so now we get 0.52 for the very first tensor. And let's go back in time a little bit, right? Here was dummy tensor, which feeds it the first row, just like we did now. We only fed it the first row. In this case, it told me that my prediction was 0. All right, if I feed it through again, now it tells me my prediction is 1. It's not really giving me anything crazy. It's just going between 0 and 1 every time I run it, right? But look at what my prediction looks like now that I've cleaned up my data. Now that I've cleaned up my data, I'm getting some sort of a more sophisticated guess, right? It's not just giving me 0 or 1. It's giving me, hey, I'm not sure if it's either 0 or 1, but I'm leaning more towards a 1 in this go around, right? And I can press play as many times as I want and notice that the data or the prediction stays consistent. Well, that's because my data is much more clean now, right? It's been manipulated, it's been cleaned, it's standardized, normalized, the whole shabam bam that we just went through. While up above, when I fed it the first tensor, I didn't do anything to the data. I just copied and pasted and filled in my null value with a 0. And because I did that, and I'm feeding essentially dirty data to my model, its predictions are consistently changing. Right? I can press play as many times as I want, and we can see it change between 0 and 1. Where down below, where I have clean data, my predictions aren't changing as often. And they're staying pretty consistent between a difference of 0.03. All right. And that is the importance behind fixing data. So let's run a quick summary over what we've done today. Today, we did a quick review up to this point of how to build our model. We talked about how we're building a binary model utilizing nn.module. We talked about our neural network, which is right here. That would accept a total of 9 neurons and output a singular neuron for our sigmoid layer. So there's our activation function for sigmoid. We established the forward pass of how a tensor would be fed through our neural network to provide an output. We then made an instance of this model and fed it a dummy tensor. We confirm the size and then print our prediction. From there, we talked about pandas, the different capabilities that come with pandas as far as being able to grab data. And we talked about the importance of standardizing and normalizing our data. We also fixed the absence of data by replacing it with a mean. And we utilized a library from SL or KL learn. Let me make sure I know this before I continue on. I know it's scikit-learn, but I always forget the extension. There you go, sklearn. All right, we imported a function from sklearn to be able to apply this concept of ensuring that our data stayed within our left and right lateral limits, utilizing standard scalar. We saw the effects that that took on our data, where it even turned some of our neurons into negative numbers. And then we talked about batching, dividing our data, again, utilizing a function from sklearn, where we establish a training and testing split, where it returned 2 batches of data, where the training batch will always be of 80%, and the testing batch will be of 20%, to ensure that our neural network is actually learning and not memorizing. All right. At this point, does anyone have any questions over any of the topics that we covered today? Let's hear it, Momo.
When we split the data into 2 paths or 4 paths, does this make difference in the accuracy?
Are you talking about batches and then difference in accuracy? So Yes, it's definitely going to train your model better with the different number of batches, and the more sample data that it has to train on and test on, the better. You do want to be careful with something called overtraining, though. If you just feed it way too much information or way too much data, it could become confused to the point where it's not making accurate predictions anymore. Does that answer your question, Momo?
Thank you. I have another simple question.
Yeah.
We imported pandas and Scikit, right? Is
Yes.
Panda and Scikit now that's considered as third parties, right? So we have two third parties here, right?
We have 3 third parties. So we have PyTorch, we have SKL Learn, and we have Pandas.
Perfect. Yeah. Thank you.
Of course. All right. Any other questions? Okay, great. If there aren't any questions, I'm going to go ahead and stop the recording here.